All right, this is 2019, number 6. National average, 1.3, which is not good, although I'll try to tell you where I think kids went wrong. The first 2 points are easy points, and so we're gonna make sure we get those, and then the backside talks a couple mechanisms. So nitrogen dioxide, NO2, is produced by a byproduct. Combustion of fossil fuels, wonderful. Elevated temperatures, it decomposes, it gives you a reaction. The concentration of the sample is monitored as it decomposes and recorded on graph below. So we've got graphs, 3 of them. They look like that on this page. This one, exponential. You've got some kind of asymptote graph. This one, linear. This one, some kind of curve there. So that guy's got some kind of asymptote looking graph, which means we know, we can anticipate that this is the answer to the question, right? A linear graph. Why people miss this is because this is concentration, that is reciprocal of concentration, and this is natural log of concentration. And I think people went concentration, natural log, reciprocal, right? Because that's what we're used to. We didn't pay attention to the fact that they did 0 order, 2nd order, then 1st order. Why did they do that? Just to mess with you, right? Because they're mean. And so it tells you here, explain how the graphs indicate that this reaction is 2nd order. The explanation is simple here on 6A. 6A. The reaction is 2nd order because a graph of 1 over the concentration of NO2 is linear. That's it. That's all you have to put. The reciprocal of the concentration is linear. Done. There's your first point. Good. Then part B comes back and says, okay, we'll write the rate law then for the decomposition of NO2. Remember, when we're doing concentrations versus times, it's integrated rate law, which means we're only dealing with one reactant at a time. And so the rate law for this decomposition, because it's 2nd order, B, the rate is going to equal baby K times the concentration of NO2 squared. That's your 2nd point. Right, and it's been a couple months since we taught kinetics, so this is one of those great ones to go back and look at and make sure you're comfy with it. Then you get to part C, and part C gives you a couple mechanisms. It says, consider the 2 possible mechanisms. Is the rate law described in mechanism 1 consistent with the rate law we wrote in part B? And so we've got a mechanism. Our first step is the slow step, which means we ignore the 2nd part of that in that mechanism as far as rates going. And so we've got 2 of those NO2s, and so it is consistent. And the explanation is the first step is the slow step, and therefore the rate determining step. It's consistent with rate equals baby K. You could do NO2s this way, because there's 2 of them that way, that's fine. Or rate equals K NO2 squared. Somehow, let's see what the question is. Is it consistent? It's consistent with this. That's probably enough there. That's answering the question. It is consistent. That's part one. And then part two gives you a second mechanism. It says, is the rate described by mechanism 2 shown below consistent with the rate law you wrote in part B? Justify your answer. So they give us another mechanism. This one, the second step, is the slow step. So the second step is the rate determining step. When we look at this guy, it's got those two NO2s, which is good, and then it's got this N2O4, right? The key here is that you have to talk about this N2O4 in the slow step being an intermediate. And the intermediate is not going to contribute to the rate. And so it's still the same consistent rate law. So yes, it's consistent. With part B. I would write the second step is the slow step. Comma, but the N2O4 is an intermediate. That doesn't contribute to the rate. And then write the rate law again. Therefore, rate equals baby K NO2 squared. Just slide up there. That's what that guy looks like. Yes, it's consistent with part B. Second step is slow step, but the N2O4 is an intermediate that doesn't contribute to the rate. Therefore, the rate equals the same thing it did before. That's it on number 6. This intermediates, when we're talking about intermediates, just on a side note, when we're talking about intermediates occur here at the activated complex. That's where you have intermediates that are forming and then breaking apart, right? They're formed in one step and then they break apart and are reused in another step. So they just occur at that activated complex. So you see some weird stuff with intermediates. You might see nitrogen by itself this way and people are always like, but that's a diatomic. Yeah, but it's in this mess of old bonds being broken and new bonds being formed. There you go. That's number 6.